Hi everyone. Today I'm going to tell you about a novel AI model called DeepFT, which is a self-supervised deep surrogate model that is specifically developed to ensure fault-tolerant edge computing using preemptive task migrations. I am Shresh Thule, a PhD student at Imperial College London, and this is a joint work with Giuliano Casale, Lucy Cherkesova, and Nick Jennings. So we all know that in the recent years, the computation paradigms have shifted from cloud backends to edge devices. Edge computing follows the data gravity principle, wherein we move the computational devices close to the end users, giving a multitude of benefits. First, it offers low response times, possibly in milliseconds, crucial for time-critical applications. Second, it solves the data explosion problem, for instance, in smart cities, where terabytes of data are generated every hour, and transferring them to the cloud is either infeasible or may require expensive networking elements for high bandwidth processing capacities. Third, it offers a closed-knit data sharing network, increasing data integrity, credibility, and security. Now, with edge computing becoming ubiquitous, it is essential to ensure that the edge nodes themselves do not become a point of failure for the running applications. And robust countermeasures are in place to incorporate overloads or failures in edge network or processing nodes. In particular, modern application demands of low latency task execution and resource constraints of the edge devices exacerbate the problem of effective resource management at the edge. The increasing volumes of data requiring immediate processing and the resource constraints at the edge are pushing the compute resources to their limits, giving rise to a high chance of resource contention and node downtimes. This leads to resource unavailability and violation of the service level objectives or SLOs that can possibly lead to significant financial losses. Further, the problem of developing robust fault-tolerant framework requires us to proactively predict faults before they occur and diagnose the root cause issues to be able to run appropriate remediation steps. For such systems to be within the strict specifications of modern industrial demands, they need to be able to resolve diverse kinds of system or network-related faults, and this may entail establishing the type of fault at the time of its prediction for a more informed recovery decision. And this may be hard, specifically when large amount of log data may be present, and manually labeling this data becomes extremely challenging in large-scale edge computing environments. Furthermore, to avoid overlooking any fault that may cause significant adverse effects later, and to avoid the overhead of false positive predictions, such prediction models need to be extremely accurate. In this work, we target a standard heterogeneous edge computing environment where all nodes are in the same local area network or LAN. Here, tasks are container instances generated from the sensors and actuators in the Internet of Things or IoT layer and communicated to the compute nodes via gateway devices. The edge broker takes all the scheduling, management, and preemptive migration decisions, and we consider system contention type faults of resource utilization metrics such as CPU, RAM, disk, and network bandwidth. And to proactively prevent fault events in a future interval, we take preemptive container migration decisions over the active tasks in the system. And finally, we formulate a problem as a discrete time control setting where we periodically take preemptive migration decisions, say every 5 minutes to avoid faults. And we call these time periods as scheduling intervals in the rest of the presentation. So let me now give you an overview of the DeepFT model and how it works. At the start of each scheduling interval, our model takes two inputs. The first is S, which is a scheduling decision for the incoming and active tasks in the system. The second input is W, which is a sliding window of the states of the edge computing environment characterized by the resource utilization characteristics of the edge devices in the environment. Now, these utilization characteristics again could be CPU, RAM, disk, etc. In our model, we consider a state-of-the-art underpinning scheduler that generates the scheduling decision S at each interval. So this becomes a good starting point for our approach. Now, similar to traditional surrogate models, our DeepFT approach has a set of neural networks that produce a reconstruction of one of its inputs, which is the state sliding window. And to do this, it has a system state encoder that takes in the time series window of system states and creates a succinct encoding of the system states. It then encodes the scheduling decision in the form of, say, a compressed representation conditioned on the encoding generated by the system state encoder that encapsulates the history of system states. And we finally have a system state decoder that generates a reconstruction of the near future system states, and we also generate a prototype embedding that corresponds to a contention type fault class in a high dimensional clustering space. And these classes correspond to CPU, RAM, disk, and network contentions. And in the end, to generate fault score, we consider the upward spikes of the true system characteristics from the resource utilization characteristics using the ReLU activation function. And to convert the continuous fault score to binary fault detection labels, we use the popular dynamic thresholding strategy, which is the peak over threshold, or POT. And POT is based on extreme value theory and generates a threshold for each input dimension, which finally gives us the fault table as shown by equation shown here. This architecture allows DeepFT to be modular and utilize any underlying scheduler, for instance, one that aims to minimize energy versus another that aims to minimize response time. And the objective of DeepFT is to only modify that specific decision based on the fault class predictions and use the best one finally in the approach. So this figure demonstrates how DeepFT is implemented as deep neural networks. We realize each of these four components of scheduling decision encoder, system state encoder, system state decoder, and prototype vector encoder as deep neural networks. And the system state encoder essentially performs spatial inference over the past task migrations using gated graph convolution network. And this allows us to capture the interhost dependencies rising from the new task calculations, which is the scheduling decision S. It also applies multi-head self-attention to encapsulate the resource utilization characteristics of all hosts in the system. Then a dot product attention module is used to effectively scale the approach with the infrastructure size, which was hitherto not possible in prior approaches. The scheduling decision encoder uses the output of this system state encoder, and again, multi-head attention allows us to generate an output conditioned on the window encoding and the latest scheduling decision. Finally, the encoded representation is sent to the system state decoder that generates the window reconstruction and the prototype vector encoder that generates the prototype fault class embedding. And further details on the implementation of each component, that is the encoders and decoders as neural networks, can be seen in the paper. So let me now introduce the idea of coupled simulation that we leverage in this work, which is also referred to as co-simulation in literature. A co-simulator akin to a digital twin simulates an input resource management decision and generates estimates of QoS scores to feed back to the decision model. And a typical co-simulation loop works in these 5 steps. First, we monitor a real system to generate characteristics such as resource utilization metrics of hosts that characterize the state of the edge computing environment. Second, we send the monitored metrics to a decision model, which in this case is DeepFT. Third, we send the system state with the sample decisions to test to an event-driven simulator that quickly generates QoS estimates for each decision. And four, we send these QoS estimates as feedback to tune the decision model and perform online optimization of the decision. And five, we enact the best decision of the decision model in a physical setup and continue this iteratively in a discrete time control setting. I shall now discuss how we train the DeepFT model. We do this in 2 phases, offline training and online tuning. In offline training, as discussed, the reconstruction of the system state window is trained using the mean square error between the predicted and ground truth windows. Further, the prototype vector encoder network is used to predict the types of faults in the system, such as CPU, RAM, and network contention. And to do this, we used a clustering-like approach with a fixed number of classes. And one of the classes was this no anomaly prototype, or NAP class. And the true cluster class was determined by the class closest to the predicted vector if fault label is positive and NAP otherwise. And the predicted class vector by the encoder network was then aimed to belong to the true fault class using what we call a triplet loss. A TSNE plot of a set of random sampled faults predicted by this model will be shown in subsequent slides. Now, once the model is trained offline on a pre-collected data set, it is critical to keep training it using new data to account for concept drifts due to changes in the workload characteristics. However, online at any time step, we do not have the resource utilization characteristics of a future time window. And to resolve this, we leverage what we call co-simulations that we described previously to generate self-supervision labels. So a co-simulator can virtually execute the scheduling decision S on the current state of the environment and generate the utilization characteristics and consequently the WT plus 1 that is required in the mean square error loss for training this surrogate model. And this is what we use to generate the time series window for a complete time step at a future interval to be able to train this new neural network on demand. And to update the scheduling decision S or ST at any time step, we define the optimization loss as follows. And this is a linear combination of the fault score and the distance between the no anomaly prototype NEP class. And optimizing using this loss minimizes the fault score and updates the prototype vector to move towards the NEP class. And as we update the scheduling decisions to minimize this loss when converged, we hypothesize that this decision should facilitate fault avoidance. And to optimize the scheduling decision, we can use the stochastic gradient descent, wherein a TSNE visualization has been shown on the right. And in practice, we use variants of the stochastic gradient descent to avoid getting stuck in a local optima, details of which are described in the paper. And finally, we see that the prototype vector belongs to the no anomaly class and hence expected to not lead to any contention-like faults. So this figure visualizes how an attention model facilitates improved fault detection. Using a self-supervised dataset to train a DeepFT model, this figure shows the time series of the resource utilization metrics, such as that of the CPU of hosts, as line plots in black, and the faults are shown in blue, and the predicted fault labels are shown in red. As is apparent from this figure, the attention scores are highly correlated to the peaks in the data, which demonstrates that whenever there is a higher resource utilization in a host and possibility of a contention, the attention scores and subsequently the fault labels are positive there. And using attention in DeepFT enables it to focus on specific hosts in the system and facilitates scaling to large number of hosts in a large scale edge setup. To test the efficacy of the DeepFT model, we run our experiments on a cluster of 16 heterogeneous Raspberry Pi devices. For our workloads, we use the popular AI-based DFOG application benchmarking suite. These include object detection, natural language processing, etc., those kinds of deep learning tasks. And we compare the DeepFT model with baselines across several metrics. For fault detection, we use accuracy and F1 scores. For diagnosis, that is the prediction of the specific host where the fault has occurred, we use the diagnosis metrics of hit rate and normalized discounted cumulative gain, or NDCG. Also, we measure the time it takes to run the fault tolerance approach relative to the time to take a scheduling decision. We call this as the overhead ratio. We also measure the improvement ratio, that is the ratio of intervals where the new decision was actually better than the decision from the underlying scheduler, which is again tested via simulations. And finally, we also compare the QoS metrics such as energy consumption, average response time, fraction of SLO violation rates, etc. So these results compare the detection, diagnosis, and fault classification performance of DeepFT with 5 state-of-the-art methods. The table shows the detection and diagnosis performance. And clearly, the DeepFT method has the highest detection and diagnosis scores with also higher improvement ratio, lower overheads compared to the baseline with the best detection scores, that is Topomap. Here are some results that show that the average energy consumption, response time, CPU, and RAM utilization in case of using DeepFT model are actually lower than when we use the baseline methods. These are some additional results showing that the task allocation time, number of migrations are lower for the DeepFT model, again facilitating improved quality of service. And further, the fraction of violations of the service level objectives is also lower for the proposed method. And for a more, I would say, in-depth analysis and discussion of the results, I refer you to our paper. So to summarize, we presented DeepFT, which is a self-supervised deep surrogate model to predict fault and perform preemptive migrations to ensure reliable edge computing. And the high detection and classification accuracies of DeepFT facilitate efficient fault recovery for optimal quality of service. And specifically, DeepFT achieves an improvement of 1.4%, 9%, and 37% for QoS characteristics of energy consumption, response times, and service level agreement violations. It is also able to correctly identify faults, giving higher classification and diagnosis accuracies than state-of-the-art methods. And DeepFT is able to achieve this with 6% lower overheads compared to the baseline method with the highest F1 score. And this makes DeepFT an ideal choice for reliable edge computing with time-critical applications. And as part of future work, we propose to extend DeepFT for fault tolerance in stateless, serverless applications at the edge, possibly requiring different kinds of preemptive migrations or different levels of granularity of decision making, which we consider as part of future work. Thank you for your kind attention. All our code and datasets are available on GitHub under BSD license. For any questions, please feel free to email me on s.tully20@imperial.ac.uk. Cheers.